Welcome to Securing Your Software Supply Chain on Kubernetes with Sigstore. So a little bit about me. My name is Priya Wadhwa. I'm an engineering manager at ChainGuard, which is a startup that focuses on securing your supply chain. I also sit on the technical steering committee for the Sigstore project, which we're going to be talking about a lot today. And previously, I've maintained a variety of Kubernetes developer tools. Maybe you've used some of these before. They include Minikube, Scaffold, and Canico. So to set the stage, why are we talking about supply chain security today? In the past few years, supply chain security attacks have been on the rise. You might recognize some of these really popular attacks that hit the mainstream media. Attacks like Log4Shell, SolarWinds, and CodeCov. And to me, the interesting thing about all of these attacks is that while they're all supply chain attacks, they're each very different. Take the case of Log4Shell. This was a vulnerability in a popular Java logging package that developers would pull into their applications unknowingly and be exposed to. In the case of SolarWinds, attackers were able to gain access to the SolarWinds build system and inject malicious code during software build time. And CodeCov was very different. It was a case of stolen credentials. Attackers were able to gain access to the credentials for the CodeCov GCS bucket and replace CodeCov's actual install script with a malicious one. The interesting thing to me is that each of these attacks are all so different, and that's because a typical supply chain has a lot of different components and therefore a lot of different points of risk. It's important to have a multifaceted approach when it comes to securing your software supply chain, and it's becoming increasingly important because governments are even beginning to take notice and starting to put out regulation for how secure a software supply chain must be. So your actual software supply chain probably looks a lot more complicated than this, but we have a classically typical one here, just to sort of illustrate the different places that risks can happen. So on the left-hand side, you have your source code. This is probably just the code that you've been writing, and whatever code that you know about that you have probably reviewed. It moves into a build system, which is where you pull in third-party dependencies. A lot of these dependencies are open source, and you probably don't know every single line of code that is in these dependencies. There's a chance you're pulling in dependencies you don't even know that you're pulling in. These two things are compiled in your build environment into some piece of software, and then packaged up and distributed, either to a consumer or in some sort of deploy environment. And at every stage of the supply chain, there's a different risk of attack. So today we're going to be talking about signing software specifically, and how it's a piece of the puzzle in securing your software supply chain. There are a lot more things you have to do to be very secure, but today we're going to be focusing just on signing and verifying software and some of the benefits we can get out of doing it. So before we get into it, I want you to think about your Kubernetes cluster. So this could just be like the one that you run on your laptop with Kind, or it could be the one that you're actually running in production. And I want you to think, are you able to answer some of these questions? Who built the images in my cluster? Where were the images running in my cluster built? What source code went into my images, including the dependencies? And what vulnerabilities are running in my cluster? If you can answer all these questions, that's actually really amazing. It's rare to find someone who can. But if you can't answer all of these questions, hopefully by the end of the talk, I will have convinced you that it's actually pretty easy to be able to get this information. So this is where Sigstore comes in. Sigstore is an open source project that was started about 2 years ago. It's part of the Open Source Security Foundation, and the goal of Sigstore is to make signing and verifying software easy. And the way that it does this is it removes the need to manage long-lived keys. If you've ever signed anything before, you probably had to generate a public-private key pair and sign something with your private key and then verify it with your public key. The challenge to this is it means it puts the burden on the maintainer to keep their private key safe and secure, and in my case, not to lose it, because I definitely lose my private key. It also puts the burden on the maintainer to figure out how to distribute their public key. How do you get it in the hands of the end users who are actually running the software? And what is the likelihood they're actually going to verify the signature? Sigstore removes this by taking away the need to manage long-lived keys by instead tying signatures to your identity rather than a public key. It does this by using the OpenID Connect protocol. I'll go more into this in the next couple of slides. Sigstore is also transparent and auditable, so you can always see a list of everything that Sigstore has ever signed and go back and see what signatures have happened in the past. The components of Sigstore are FullSEO, which is the Sigstore Certificate Authority. FullSEO is responsible for issuing short-lived code signing certificates to users, which basically eliminates the need to manage key pairs. The record is a transparency log, which is append only and immutable. This is where we store a list of every signature certificate and signature that Sigstore has issued, which allows it to be transparent and auditable. And finally, cosign, which is the CLI tool used for interacting with Sigstore. As a maintainer or an end user, this is all you really need to start signing and verifying your software. So the goal of Sigstore really was to, in particular, secure open source. There are so many open source dependencies that you're pulling in that you may not know about. And it's important to start securing them, and signatures are an easy way to get started. Kubernetes images themselves are actually signed by Sigstore today. And we are in the works to start signing NPM packages and Python packages. Hopefully, over the next couple of years, we'll be able to start signing all of the major package systems with Sigstore as well. So how does this work? So excuse my poor drawing skills, but we have a maintainer on the side, and all they need to sign their piece of software is the cosign CLI tool. What this maintainer is going to do is run the cosign sign command and then pass in that piece of software. It could, for example, be a container image. Cosign is going to direct the maintainer to this browser flow, this OAuth browser flow, where the maintainer will log in with their email. This is how the maintainer proves their identity. You've probably done this a bunch of times when logging into, like, I don't know, Spotify. So the maintainer will log in with their preferred identity provider, and that identity provider will return an identity token to cosign. Cosign will then send that identity token to the FullSEO Certificate Authority, which will validate it and issue a certificate. Under the hood, cosign is also going to generate an ephemeral key pair. So we like to call this keyless signing in quotes, because technically you never need to generate the key pair yourself. But cosign will generate a temporary ephemeral key pair in memory, which will never hit disk and is only really exists for the duration of this signing. Cosign will sign the piece of software with the private key and embed the public key in the certificate. In addition, the certificate will actually contain the email address that you signed with. So this is how we bind your actual identity with your signature. The idea is it's easy to lose a private key, but it's hard to forget your email address password. So the final step of this is that the certificate and the signature are stored in the record transparency log, which is a completely public, cryptographically verifiable log. It's append only and immutable. So once there's an entry in the log, it can never be changed and it can never be deleted. And if something is tampered with, anyone with access to the log, which in this case is everyone because it's public, anyone can cryptographically verify that it has been compromised. So this is an example FullSEO certificate which has been issued. So you can see at the top, we have some information about how Sigstore has issued the certificate. The certificate itself is actually only valid for 10 minutes. It's a code signing certificate, and you can see that embedded in the certificate is my email address and that the issuer was Google, if I signed in with Google. Signatures are great, but they're ultimately useless if they aren't verified. And so the other main goal of Sigstore is to make it as easy as possible for end users to actually verify this software. And luckily, all the end user needs is the same two things that the maintainer had, the cosign CLI tool and the same piece of software. If we run cosign verify on this piece of software, could be a container image or a binary or anything, under the hood, cosign will retrieve the correct transparency log entry from the log. It'll validate that the certificate is valid, by verifying the public key embedded in the certificate against the signature. And all the end user has to do is confirm that the identity associated with the certificate is one that they trust. So with this, we can actually answer this question: who built the images in my cluster? If I can verify my image and I can see in the certificate the identity that signed this piece of software, I can answer this question. Let's move on to the next two. Where were the images running in my cluster built, and what source code went into my images? So we can actually use Sigstore to help answer these questions as well. The nice thing about Sigstore is that both people and systems can request full CO certificates. I'm guessing that you're probably not building your software on your laptop, which means you wouldn't really be able to sign it just on your laptop either by always going through that browser flow. The nice thing is any CI/CD system that supports the OpenID Connect protocol can also request certificates from full CO. So we have support for GitHub Actions, GitLab, and I think we have Circle CI in the works as well. You can also sign using request certificates using Kubernetes service accounts, and if you have Spire running in your cluster, you can use that as your identity provider. If we take a look at this distroless image, which has been signed in a GitHub Actions workflow, we can see that additional information was actually embedded in the certificate. The issuer is GitHub. The subject actually points to the exact repository and GitHub Actions workflow that was run. We put in the run attempt number, the run ID number, and the exact commit SHA that this workflow was run at. So we can actually tell exactly what repository this image was built in and exactly at what commit SHA. So we can tell what source code went into it. So this is an example of a certificate issued to a GitHub Actions runner. You can see that in the subject, instead of an email, we actually have a lot more information around the actual GitHub Actions workflow, plus some additional metadata, like I said, at the bottom. Finally, we might want to answer a question: what vulnerabilities are running in my cluster? It's important to know if any critical vulnerabilities are in your cluster so you can remediate them as fast as possible. So the nice thing about Sigstore is, in addition to signing your images, you can also sign related artifacts like vulnerability attestations and attest them. So we can use tools like Trivia or Gripe to generate vulnerability scans, and then use Sigstore to actually sign those scans and upload them to our repository alongside our image. This doesn't actually need to be limited to vulnerability scans. You can also upload things like SBOMs or any sort of metadata around your image. But today, I'm going to be talking about vulnerability scans specifically. So let's do a quick demo. So I've got this GitHub repo, and I've got a pretty simple GitHub action running. So I'm going to kick it off since it takes about a minute, and we can walk through the workflow file while it goes. Let's hope that this one works. It's worked every other time that I've done this, so we'll see. So I've got my image, which is just being pushed to my GitHub repo. And we have a few steps. They're pretty simple. We're installing the Sigstore cosign tool, which we're going to use for signing. Instead of building the image to save time, I'm just actually going to copy the Docker Hub Nginx image to my own repo. We're going to sign it with a cosign sign, and then we're going to run a vulnerability scan on the image. Note, in the format field, I've specified that I want the format to come out in a format that cosign can understand. The last step, we're going to actually attest this vulnerability scan. So we're going to sign the vulnerability scan itself, upload it to our repository alongside the image. So if we take a look, this might need a few more seconds. Cool. So we copied the image, the Docker Hub Nginx image, into my repo. We signed that image with a cosign sign command. You can see that an entry was created in the transparency log associated with this image. We ran the vulnerability scanner, and then we attested that scan. So this basically signed that payload, the vulnerability scan, and uploaded it to our repository. This is the certificate that was issued, and this is the entry in the transparency log. If we head over to my terminal, we can try to verify these things now. So I've actually saved the command because it's quite long. to show you. So to verify the image first, the signature on the image, we pass in the name of the image, the name of the expected identity of the certificate, which is my specific repository and the exact workflow that we ran and that we built it in, and then the expected issuer, which is GitHub. And you can see that it outputs a bunch of information, but the verification was actually successful. If we pipe it through JQ, we can make it a little bit more pretty. And you can see now, as anyone who is running this image has access to all of this information. So they can see that it was signed, exactly where it was signed, what commit it was signed at, and exactly what the repository was. But we had also signed that vulnerability scan. So let's see what that looks like. It's a really similar cosign command. Instead of cosign verify, we're going to run cosign verify attestation. And we get a bunch more output. It's also quite big. But similarly, the verification has succeeded. Let's pipe it through JQ. We can see, oh, sorry, this is way too long. I'm going to extract out the payload from here. It's base 64 decoded, pipe it through JQ again. So we can see the actual vulnerability scan that was run now, just by running cosign verify attestation and the name of the image. Anybody running this image now has access to this information and knows exactly what vulnerabilities are in the image itself. Excuse me. Great. So the Sigstore is actually free for anyone to use, and we maintain a public instance for anyone to start signing and verifying their software. We announced general availability for all of the public services last year, and there's actually a 24/7 on-call staffed by Sigstore maintainers. And if I could ask a favor, please don't slam it right now because I'm actually on call. Great. So how can we use this information, this metadata around our images to actually secure our Kubernetes cluster? So this is where the Sigstore policy controller comes in. The policy controller is an admission webhook for Kubernetes, and it allows you to write really powerful policies around supply chain metadata in either the Q or the Rego policy languages. It's easy to install via Helm, and it allows you to say things to enforce policies like these in your cluster. You can say things like, I only want to run containers from specific registries, or I only want to run containers built in my CI/CD system. I don't want any critical vulnerabilities, or specifically, I don't want log4j running in my cluster, if that's something that you're concerned about. And the way that we do this is with the cluster image policy CRD. So once you've installed the policy controller, which is just a webhook in your cluster, you can actually start writing really powerful policies by using the cluster image policy CRD. The first few lines you probably recognize, like classic Kubernetes YAML. But the images and the authorities is really the key part of this policy. In the images area, you can specify the exact images you want this policy to apply to, and then in the authorities, you can specify exactly how you want to validate these signatures. Whether in a keyless flow, this would be the issuer and the subject that you expect to have signed the images. You can also pass in just a public key if you were using a key pair for signing. So this is actually a valid policy to validate all of the Kubernetes images. This is the actual service account that they use to sign their Kubernetes images in the Kubernetes release flow. So it can be a little bit hard to know how to get started with writing some of these policies. So we do have a policy catalog, which is an open source catalog of common policies designed to work with Sigstore and Policy Controller. For me, I never really have learned how to Q or Rego, and it's a great place to start with a lot of the kind of things you might want to do. So here we have a slightly more complex policy. This is the one I'm actually going to be running in my next demo, where we say that all images running in our cluster must be signed. Specifically, they must have been signed within my own GitHub Actions workflow. So let's take a look at that. So if I head back to my terminal, actually, let's take a look at some policy catalog examples first. So here's an example of just the same one I showed earlier. All images must be signed, and these are the identities that must have been used for the signatures. We have a slightly more complicated one here to say that there must be no high or critical CVEs running in our cluster. So when we try to run the image in our cluster, the policy controller will go in, check that vulnerability scan for us. If there's any high or critical CVEs, that image will be rejected. And you can also actually write policies just around best practices for Kubernetes security itself. So this is a policy to make sure that there are no host path volumes allowed in your cluster. So if we head over, I have policy controller running in a kind cluster right now. We can apply one of these policies. So this is the one to make sure that all images have been signed from my GitHub Actions workflow. So I can apply this. So now if I try to run the Docker Hub Nginx image, it should fail since it was not signed within my own workflow. Let's give it a second. Great. So no signatures were found. So this was denied. Now, if we actually try to run the image that I had just signed in the workflow in the first demo, let's see if that passes. Policy controller does require that all images are specified by digest. So I'm going to grab the digest for that image first. Oops, 2 Ds. This is supposed to be kube control. Great. As you can see, it was accepted. We can also now apply the policy to make sure that there are no high or critical vulnerabilities in our cluster. So I'm going to apply that. Now, if we try to run the same image, I'm guessing this is going to fail because typically the Docker Hub Nginx image does have some vulnerabilities in it. Yep. No shade, sorry, but there were 3 high vulnerabilities, so that was rejected. Great. So what can you do next? For your own software, I would definitely recommend checking out Sigstore and try signing with it today. There's actually a free course provided by the Linux Foundation if you want to learn more about the architecture and how it works. And also try out Policy Controller for verifying images in your cluster. You can actually just start by verifying the Kubernetes images, since those are already signed. And we actually have a tutorial for setting it up on a kind cluster if you just want to try it out locally first. Thank you so much. The Sigstore project is an open source project, so if you're interested, want to contribute, or just want to learn more, check out sigstore.dev or our Slack channel. We welcome contributors all the time. Thank you. Oh, yeah. Any questions?
Oh, over there.
Hi, great talk. I had a question on the policy controller. You mentioned it's an admission controller.
Uh-huh.
Is it also able to check if new vulnerabilities appeared for workloads that are already running, or is it only at admission time when you're deploying the new workloads?
It's only at admission time.
Okay, thank you.
Nice.
If I want to use it in-house and combine, let's say, images I've signed internally, I don't want to put the information out to the Sigstore and then having that somehow combined, let's say having an internal log and the external. Is that easy possible to combine?
It could work. I think the log, you could run Sigstore itself internally as well. Like you could set it up privately for yourself if you don't want to use the public log. I think it would just have to be Sigstore compliant to work with Policy Controller specifically. It also depends on how you're signing. If you're just signing with like a key pair or a KMS key, then you can just pass in the public key itself, and we can do the verification.
And if I use just expose the JWKS endpoint of my issuer, but it's not, the rest is not exposed, that's sufficient to verify if I was signing.
It should be. You probably have to set up full CO on your own, since we only support like a few identity providers right now with the public instance, but it could work.
Cool, thanks.
Maybe one question. Maybe just a follow-up thing. Let's say, I guess it will be extremely successful, but Sigstore, goes out of business or some disaster scenario happens. So what do you foresee in this kind of scenarios, or just summary?
Yeah, that's a great question. I mean, it really does depend on the log always being up to be able to constantly verify anything that's been added to the log. I don't have a great answer for you. That really would be a disaster scenario. But I guess all you could do in that case is set up some sort of like break glass mechanism for your cluster so that you can start admitting things that where the signature isn't working or verifiable anymore.
Thank you.
I have another one. Why you're storing, let's say, the 3V output there and not the SBOM? Because maybe later on I want to recheck based on the SBOM the vulnerabilities and not what happened or what was the state of the build time.
I would highly recommend storing the SBOM as well. The reason I did not show that is because I only had 30 minutes.
Okay. Cool, thanks.
Great. Awesome. Thank you. Feel free to find me if anyone has anything else.